Consider the following question. We've all, at some point, gone and got some kind of drink from maybe Starbucks or Dunkin' Donuts or McDonald's, something like that, and you get a cup like this, and sometimes they'll have a top that sort of snaps on. It looks like a hemisphere kind of. It's got a little hole up here, and you can put your straw through, and you snap this top down onto the top of the cup. Well, look, there's two different manufacturing processes to produce these two items. Obviously, we need to be careful that the top cup is the right diameter to fit on, the lid that is the right diameter to fit on the top of the cup. All right, so let's make up some hypothetical facts here. Let's pretend that the upper diameter, or the diameter of the top of the cup, is a normally distributed variable with a mean of 3.96 inches and a standard deviation of 0.01 inches. Okay, it's kind of a wide cup there. And then let's pretend that the lids are also created or distributed normally, and their mean diameter is 3.98 inches with a standard deviation of 0.06 inches. And you get this little thought, that seems reasonable. I mean, the diameter of the lid might be a little bigger than the diameter of the cup, so it could fit over the top of it and snap onto it. If the diameter of the lid were smaller than the diameter of the cup, it would never fit over the top. You wouldn't be able to place it there. So we know we don't want that. Okay, but it turns out there's one more requirement, and that is the lid will only snap onto the top of the cup if the difference in diameters. Now let's give these things some names. We'll just say the lid minus the cup is less than 0.06 inches. It turns out that that's going to be the requirement. Okay, and it's also going to have to be greater than 0, because if for some reason the lid minus the cup, this value in the middle, were negative, that would mean the diameter of the lid was smaller than the diameter of the cup. It would never snap on. All right, so this is what we're looking to find. We know that these two variables up here are normally distributed, and that's helpful because we like normal distributions. We know how to do z-scores and find areas and use our charts. Okay, so how do we do a problem like this? Well, what we need to do is create a distribution for a new random variable, the lid diameter minus the cup diameter. That's what we need to create. We create that random variable, then we can answer this probability question, the probability that this occurs. All right, so what do we know about random variables? Well, we know we can add and subtract their means. So the mean for the lid minus cup distribution would be mean for the lid distribution minus the mean for the cup distribution, which in our case is 3.98 minus 3.96, or 0.02. All right. Now, we also know that we're not allowed to add or subtract standard deviations. We can only add variances. So if our goal is to find a standard deviation of the lid minus cup distribution, we need to start with the variances. So we'll start by finding the variance of the lid minus cup distribution, and that's going to equal the variance of the lids plus the variance of the cups. Okay, we can only add variances. There's a reason for that, but it's a little too long to explain here. For the time being, just know that. Well, we know that the standard deviation for the lids is 0.06 inches, so the variance for lids is 0.06 inches squared plus. For the cups, the standard deviation was 0.01, but the variance would be 0.01 squared. So we do that calculation, we get 0.0037. Now be careful, that is not the standard deviation. That is the variance of lids minus cups. To get the standard deviation, we're going to take the square root of that. So we need the square root of 0.0037, and that is 0.0661, I guess. We'll round it like that. Okay. So now we're ready. We can start to create a picture of our distribution and shade in the area that we're interested in. So what do we know? Our lids minus cups distribution looks like a normal distribution. In the middle, its mean would be 0.02, and we know the standard deviation is about 0.061. Okay, so we also know that the lid will not hold onto the cup if it's between or greater than a difference of 0.06. So we want the following. We want to make sure that we're between 0 and 0.06 under this normal distribution. And that's something we can do because we can find z-scores for both of these and use our charts. That's what we're going to do now. So the z-score is 0 minus 0.02 over 0.061. And that's my lower z-score. My upper z-score is going to be z equals 0.06 minus 0.02 over 0.061, which gives us, in each case, negative 0.327. 327, sorry, that's a sloppy 2. And over here, 0.0656. All right, so what we also can do now is we can go to our normal distribution chart and look up the areas associated with each of these z-scores. So here, this area associated with this z-score, which is all of that stuff, turns out to be about 0.7454. Over here, this area, to the left of 0, turns out to be about 0.3707. So now we know the desired area, the probability we really want, the probability that 0 is less than lids minus cups less than 0.06 would equal 0.7454 minus 0.3707. And we get an answer of about 0.37. Well, that's a little bit concerning. If you think about it, that means only about 37% of the time will this lid snap onto this cup. I'm willing to bet that big companies like Dunkin' Donuts, McDonald's, things like that, companies are going to utilize this company would probably say, hey, wait a minute, the time, there's too many times when the lid doesn't fit onto the cup. You guys need to correct this process. That's the consequence of making up these numbers. I'm sure somewhere we're able to attain the real numbers. I'm willing to bet that the probability that the lid and the cup fit is probably very, very, very close to 1, almost perfect. Because every time this doesn't fit, it's a potential item that they might have to throw away. It's something they paid for. Okay, thanks for watching.